Hello guys, so welcome back to our third lecture. This is actually the third part of the third lecture and the final part of it actually as well. So in the first two parts, we explore the basic, axioms and or postulates and the theorems in Boolean algebra. And now the question, why we learned such axioms and theorems. Basically, this is your first tool to evaluate and minimize a function, a Boolean function. Okay, something like this. So here we have f, which is representing a Boolean function, a function of in x, y, and z, three other Boolean variables. Okay. So we have here the evaluation. We should evaluate the function, and to evaluate a function, we drive its truth table. This genius idea of the truth table that represents the whole space of a function, because basically here, as again, each Boolean variable is just two values, either 0 or 1. Okay, so we have three variables. So three variables, each one can take either 0 or 1. So we have 2 to the power of 3 different combinations. Okay, starting from 0, 0, 0 until 1, 1, 1. Okay, so to evaluate the function, we should, at each combination, substitute in the equation here, this Boolean equation, and get the value of f. So for example, at 0, 0, 0, so 0 for x, or z is also 0, and y is also 0, but we want y bar. Don't forget the bar here. So we represent the bar or the complement as a prime like this, or use this upper bar. Okay. So y bar will be 1. So 0 or 0 and 1 is 0. So this will be 0. And you can do the same for other parts as well, so other combinations as well. But I want you to be smarter. Okay. So basically, f is equal to x plus y 0. Okay. So if x equal to 1, so f will be equal to 1 or z y bar. And we know that from the axioms and the theorems that we learned, it's that 1 or anything will give you 1. So just look at here. You have here 4 cases in which x is 1. So basically f will be 1 as well. Okay, that's very nice. Then if x equal to 0, then f equal to zy bar. Okay, it's an AND gate. Okay, so just look, if z is equal to 0 now, then f for sure will be 0, whatever y bar is. So here you have x z equal to 0, and here you have z equal to 0. Of course, we are concerned now about the first 4, because in these first 4, x is 0. So for these two, f is 0. Okay, good. Now when z equal to 1, at that time we just look at y bar. Okay, and we want y bar to be equal to 1 in order to make f equal to 1. And that means y should be 0. So at y equal to 0, we have f equal to 1. But if y is equal to 1, then y bar will be equal to 0. So f will be equal to 0. Okay. This is, a detailed, smarter way to do it. When you train yourself a lot, you will find it easier. Okay. But please don't go, in each combination. Always think that these, you have these axioms always in your mind, which will simplify a lot of things to you. Okay. Okay. Now we evaluate f. We know the values of f. Okay. When f equal to 0 and when f equal to 1. Okay. Now we want to implement, if we want to construct a circuit, a digital circuit that represents f. Okay, just look at the equation. Okay, it's x or z and y bar. So basically we need y bar, not y. So we need inverter. So the output of this inverter will be y bar or y prime, which is a complement of y. Then we need an AND gate to AND z and y bar together. Then we need an OR gate or x and y z bar. Okay, so we have here, you know, three gates. Three gates. We need one OR, one AND, and one inverter. Okay, you know, in the future, we will not be concerned a lot about the inverters. Okay, we will just count AND and ORs, and we leave, you know, we will ignore usually the inverters. So we need here, you know, two gates, AND and OR gate. Basically, yes, we need inverter, but you know, in the future we'll just ignore the inverters. We'll be more concerned about the number of AND and OR gates. Okay, another example. Example 2, f equal to x bar, x complement, y complement z, or x complement zy, or x y complement. Okay, again, we have the truth table here. We have again three variables, although we have a lot of terms now. We have three terms, not just two terms, like if the first example. Okay, but you know, same concept. Since you have three variables, you only have, you know, 2 to the power 3, which is 8 combinations. Even if you have, you know, hundreds of these terms. Good. Again, to evaluate this, okay, you can go one by one, combination by combination, okay, or you can again, you know, use your, you know, intelligence to, you know, simplify it more. Okay, so let's see here. If we have here x bar, y bar, z, x bar, zy, x, y bar. So basically here, if x equal to 0, if x equal to 0, then f will be equal to y bar z plus or you know, zy, and if x equal to 0, the final term will just go away. Good. So you have y bar z, yeah, and then we can take z as a common factor. Remember the distributive, you know, property. So this will give us, you know, y bar plus y, and if you remember, y bar plus y is equal to 1 all the time. This was one of the theorems, one of the axioms. I can't remember, but you know, the result is 1. So this will be equal to z. So whenever x equal to 0, f equal to z. So here is x equal to 0, and here is the corresponding z. 0, 1, 0, 1. F is just z. 0, 1, 0, 1. Okay. Then, you know, you continue approach. You try to simplify the circuit. I'm sorry, the expressions that you have, you know, for each value of x, and see, let's say x equal to 1. What's going to happen? When x equal to 1, okay, then x bar is equal to 0, or x prime equal to 0, or the complement. So basically, you don't have the first two expressions. So f equal to x y bar, and remember x now is 1, so this will be y bar, or y prime, or y complement. So when x equal to 1, you just complement such 4 values. So 0, 0 will be 1, 1, 1, 1 will be 0, 0. Okay, good. This is for the evaluation, the truth table. Now for the implementation, we have here 3 terms. Let's, you know, remove this example here. I was explaining before. You have here 3 terms. This number 1, number 2, number 3. The first one can be implemented using one AND gate with 3 inputs. So this expression has 3 literals. So we name each variable in the term literal. And the literals in a term is actually the number of inputs. So it is number 1. You see 3 inputs, x bar, or x prime, bar, y prime, and z. Here's the second one, x prime, zy, and here is the third one, xy prime. Okay? Then we need to add all these terms together. So the output of the first is the output of the first, second output, third output, all of them are ORed using this OR gate. So don't say that we have an OR gate here and the OR gate. No. So you can consider it as follows. You can say that, let's say the first term is called K1 equal to x bar, y bar, z. Second term is K2, x bar, zy. Third term, K3 is equal to x, y bar. So f is equal to K1 or K2 or K3. So you have, one OR variable, one OR gate, I'm sorry, which has 3 inputs, K1, K2, K3, something like this. That's why you need just one OR. Don't look at here and say, oh, we have 2 ORs. No, it's one OR. And each term is considered as input to that OR. Okay, good. And it's easy to implement, OR gate with multiple inputs. So one fact here is that this implementation is valid. I mean by valid that we have only one OR, not multiple ORs, because in real hardware you can implement an OR gate. You can have a circuit, I mean, that has that represent OR gate with multiple inputs, more than 2 inputs. Okay, that's why we used only one OR gate. If there is a restriction that there is no circuit, real circuit that represent OR gate with more than 2 inputs, then for sure you will not use you will use more than one OR gate, for sure. But fortunately, we have such circuit that represent OR with multiple, more than 2 inputs. Okay, that's good. But can we do better? And actually, yes, we can do better. Basically, one step here that I ignored in that example 2 and the example 1, is to try to minimize the function first. And this minimization will lead to smaller circuits, smaller components, cheaper circuits. So let's do that. So let's go. So basically here, we should do algebraic manipulation for our, function each time to try to minimize, the number of logic gates that we're going to use in the final circuit in the implementation. So let's go to our example. This is the second example that we just implemented. And as we see here, we used gates. 3 and 1. And again, we will not count those inverters. Okay. So let's try to minimize this using the axioms and the theorems that we discussed, in the first 2 parts of this lecture, and see if we can get a better, or similar form or similar expression and similar, or number of elements for f, this function. Good. So let's try to do that. So basically here, just to compare the first 2 terms here, you have here x bar, you have here x bar, you have here z, you have here also z. Then what's different is that here is y bar and here is y. Good. So just like a normal, decimal algebra, we can say, or the normal algebra that we knew, we can take x bar z as a common factor. This is actually the distributive property, but in an opposite way. So basically here, f equal to x bar z, then y or y bar, then or x y bar. Good. And we know that y or y bar is always equal to 1. So this term here is equal to 1 all the time. So basically f is equal to x bar z or x y bar. That's much simpler than the first one. Okay, so let's implement this. So basically you need, two AND gates. The first one has x bar and z. The second one has x and y bar. Then you OR them together. Then you get f. Okay, what we needed here, we needed two AND gates, one OR gate. So let's check the first one. The first implementation, C AND gates, one OR gate. And there is still a difference. These AND gates here, should have three inputs. So these are three inputs and gates and three inputs or gate. Okay, but here it's only two input and the two input OR. And usually the circuit that has less number of inputs, is easier to implement and has less restrictions. Okay. And we saved again one gate. Actually, this is 25% because we have in the beginning 4 gates. When you take one, it's 25% reduction in the cost. And remember, each one of these are just a circuit. Circuit means it needs a VCC and a ground. If you have the same VCC everywhere, so here the VCC is feeding 3 circuits. Actually 3 simple circuits because we reduced the number of. But here the VCC is feeding 4 circuits, actually 4 more complex circuits because they have 3 inputs. So our minima here can reduce also the power consumption, not just the area and the cost, but also the power consumption. Okay, so minimization is a very primary step, or elementary step that you should do all the time. The first example has no minimization, that's why I will not touch it. But the second one that we will, here with 4 gates, if we try to minimize it, we will reach to a simpler design. Good, so let's continue. Let's have more examples. Yeah. So let's try to do that. Here, I will not do the truth table anymore. I will just concentrate on the minimization and the implementation before and after the minimization. Okay. Let's implement this without any minimization. Just take it as granted that it's good. Okay, and see. So you need AND gate. This AND gate has input as X, and the other input came from an OR gate that take X bar and Y. So we need 2 gates. Okay, good. But let's try to minimize it and see if we can reach simpler form. So if equal to, let's distribute X over the brackets. So this will be X bar and X bar or X Y. What is X bar? This is 0, if you remember one of the axioms. So this will give us X Y. And that's it. No other minimization can be done. Let's now implement this. This is just one gate, X and Y. Oh, one may say, I'm not convinced with this. How this circuit can give me the same output as this? They are these two different circuits. Yeah, but they will give you the same output. Remember, we are here in another domain. Here we are dealing with Boolean variables with 0 or 1 only. This is not real circuits, real numbers we can say, or with infinite values. So this is basically a byproduct of the of the properties of Boolean variables. And if you're not convinced, you can just do the truth table of both. So what we need to prove now, okay, although it's proven, by this algebraic manipulation, but let's prove it by truth table. Why? This is a basic definition that nobody can argue about. So let's prove that this is equal to this. What you need to do is to have x and y, 0, 0, 0, 1, 1, 0, 1, 1. Then you have x, y. So let's do it with another color, like for example, red. Let's go for magenta. 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, and 1 and 1 is 1. Good. So this is, we get this. Now we get this. So you can do, okay, x prime or y. Okay, you don't need to do another column for x prime, by the time you will get used, just to make it in your mind, think, apply it just on the paper. So x prime is 1, 1 or 0 is 1, 1 or 0, 1 or 1, I'm sorry, is 1, 0 or 1, 0, I'm sorry, 0 or 0 is 0, then 0 or 1 is 1. Let's do it again just to verify. So x prime will be 1, 1, 0, 0. So 1 or 0 is 1, 1 or 1 is 1, 0 or 0, 0 or 1 is 1. That's right. Okay. Then x prime or y. So just add this column with this column. 0 and 0 is 0, 0 and 1. I'm sorry, 0 and 1 is 0, 0 and 1 is 0 again. 1 and 0 is 0, 1 and 1 is 1. Now compare this by this. This is equal to this, this is equal to this. This is another proof. This is just to verify that, a check, okay, that really this minimization work. And it greatly reduces the number of, here is 50% reduction. Remember, here is 2 gates. It tends to be just 1 gate that we need. And both functions are just equal. So this is equal to xy. Okay, good. Let's see another example. X or x prime y. X or x prime y. Good. So let's distribute. Now this is again, this is Boolean numbers. It's Boolean algebra. So I have a new, rule here that you can distribute even with or. So this is equal to x or x bar. I mean, I would distribute x over this term with the or here. So this is equal to x or x bar and x or y. What is x or x bar? It is just 1. This is just 1. So 1 dot x or y. This is actually equal to x or y. Let's implement the first one. So the original form is x, and you need here an AND gate between x bar and y. Then you need an OR gate to OR them. How about this? This is just one OR gate. Again, 50% reduction. But wait a minute. You remember, guys, the duality principle that we touched in the last slide of last lecture, second part of lecture 3. In this duality part, we said that you can reach the same formula or an equivalent formula or equivalent rule or theorem or postulate just by changing and into or and the 0 into 1. Okay, and this is actually, we don't need to do all of that, because if we look here, this is the dual form of that function here. Okay, so the dual of f is what we see here, which is x and x or y. X and x prime or y. What happened here? The or, this or is converted into and this and is converted into or. What was the result of this? We find that this is equal to xy. So by duality, we can, just before touching this, we can say just here, when we just finished this one, we can just say that by duality, we can say that x or x bar y equal to x or y. Again, we change or replace the or by and by or. If there is a 0, it change it to 1. If there is a 1, change it to 0. You will get another axiom or another theorem or another equivalent form. And that's basically what we have here. So this is a proof by duality, and here is a proof by just algebraic manipulation. But both are equivalent. You can do any of them. Good. Let's have another example. F equal to x or y and x or y bar. Okay. So what we're gonna do here? So this is basically, if you look at, this is a distributive property. So like just, but in the opposite way. So here is x and x, this is a common factor, and here is y and y bar. So you can say that this originally was x dot or and y or y bar, because this, from this we can go to this, we can just distribute x over y. I'm sorry. Okay, let's have another example. So x or y and x or y bar. Okay. This is actually, if you look here, you have a common factor between the two brackets, which is x. So this is a distributive form. Okay. But of the or, I mean, this actually equal to x or y bar. X or y bar. And we can reach this from this, by the way. So you just distribute x over this term y bar. So x or y and x or y bar. Of course, in decimal algebra, the algebra that we know all these years, we cannot do that. This is just because this is an advantage of Boolean algebra, because of the stability of Boolean variables. They are just true or false, or 0 or 1. Okay. Okay. Now y and y bar is actually equal to 0. So this is basically equal to x. No gates at all. No gates at all. Okay, this is 100% reduction in the cost and the power consumption and everything. 100%. So let's draw the circuit for this one. So we need an OR gate with x and y as input. We need another one with x and y bar as input. Then we need to AND them together. And here is f. What is the circuit of this? Just x. X is just f. And you can do it by a truth table. If you don't believe that, you can just calculate x or y and x or y bar, then AND them together, you will get same as x. I will leave it to you. Okay. Can we do something by this? Can we deduce another rule So we discovered now that this is actually equal to x. We discovered this. By duality, can we discover another type of this simplification? Yes. So by duality, if x or y and x or y bar equal to x, then x and y or x and y bar should also equal to x. But this is easier to to what to prove, because you can just take x as a common factor, then y or y bar and y or y bar is actually equal to 1. So you have the duality, and you can also do it by from scratch, assuming that you don't know such property here. Okay, let's have another example. Okay, xy or zx bar or yz. This is a little harder than the other ones. Okay. So before anything, let's draw the circuit for this, the implementation of f. So we need 3 AND gates basically. This one will take x and y. This one will take z and x bar. This one will take y and z. There's only one OR gate that have 3 inputs. This is the original implementation. But let's try to minimize this function and see if we can get a better implementation for f. Equivalent form that will give you the same truth table, same values for f, for the same combinations of y, x, y, z. Okay, but with a much simpler circuit or less number of gates. Let's see. So what we're gonna do here, I'm gonna AND x or x bar. Okay, x or x bar. Remember, x or x bar is just 1, and yz dot 1 is just equal to yz. So we don't do anything. Okay, we don't affect, the function. Just add. We just multiply one of the terms with 1, not multiply. We end it with 1. Okay, so equal to xy zx bar. Then we distribute yz over this bracket. So this will be yzx or yzx bar. And we wait a minute here. Let's now compare the terms together. Okay, so you have here xy and you have here xyz. So take xy as a common factor from these two underlying term. So xy, this will give us 1 or z. If you are not sure, just make it again. So if you just distribute xy over 1 or z, it will be xy plus xyz. Then we take these two terms and compare them to each other. Zx bar and y, you have here zx bar ended with y. So take zx bar as a common factor. So this will give us 1, this will give us 1. What is 1 or z? 1 or z all the time is 1. For million years forward, it will be 1. 1 or y, again 1. So this is basically xy and 1 or zx bar and 1. So this is equal xy or zx bar. This is actually one of the terms has just vanished. One of the terms, which basically the third term here, has just disappeared. So basically you now reduce one of the gates, one of the AND gates basically. So let's draw this. So you have two AND gates, xy. The second one is zx bar. Then you have OR gate. This is basically it. So all of this is equal to xy plus zx bar. And the third term just vanished. And we have something similar. We took something similar here. If you guys remember xy, one of the theorems, that xy or xy is equal to x. And the proof is very easy. Just take x as a common factor. It will be 1 or y. 1 or y is 1. So x and 1 is x. Something very similar here happened. Okay. Now we reduce the number of gates by 1. And also the OR gate at the output has only 2 inputs. And again, this will make its implementation a lot easier. And this will reduce its power consumption as well. And one may say, how come this circuit and this circuit are equivalent? Yes, they are equivalent. Just to do the truth table. If you do the truth table for this, it will give you the same if as this. Okay. Okay, let's have another example. Yes, this is a very nice one. Okay. There are 2 proofs for this. I will do the easier one and you do the other one. Okay. So basically, we can do that by, we can prove that by the duality. Okay. We just saw that x and y from the previous slide. We saw that xy or zx bar or yz equal to the first 2 terms, which is xy or zx bar. So by duality, we can say that x or y, we flip the and into or, we flip the or into and z or x bar and y or z should be equal to the first 2 terms only, which is x or y dot z or x bar. Okay, so by duality, by duality, from the relation in the previous slide. This is basically the proof. Okay, can we do it from scratch, assuming that we don't know, this proof here that we did? Yes, you can do it. Just follow the same steps. Follow the same steps. You might change something, but it will be the same context. And remember the duality all the time. Okay. And I leave it to you. And of course, we can prove it using the truth table. So we can, but this is now not a proof because we want to simplify it. We want to simplify that. The truth table will give you, the value of f. Okay, so it will not be a way to prove that. I'm sorry, to deduce a simpler form for f. I mean, if you given f equal to z, you cannot using the truth table get into that conclusion here. But you can prove. I mean, if somebody tells you how to prove that this is equal to this, you can do that by using the truth table or the algebraic manipulation or the duality. Now, in your assignment, you will do the algebraic manipulation. Okay. Okay, so let's have another example. Yeah, this is a good one because it will review one of the important concepts or the theorems that we discussed, which is Demorgan Theorem. Okay. So if you remember Demorgan's, it says that in Demorgan, x and y and the total is bar. The complement of this function x and y is equal to x bar dot y bar or x prime dot y prime, whatever you write your complement is, the shape of your complement, either prime or bar. So basically this will be equal to x prime or the whole brackets prime. So y bar, z bar, or yz, and this is totally part. Okay, good. So this is equal to x bar, or then here you will have two brackets, y or z, then y bar or z bar. Okay. Can we do more? Yes, we can do. So this is equal to x bar as it is. Then distribute y and z over this bracket. So this will give us y bar or y z bar, then or zy bar or z bar. This is equal to 0. X and x bar is equal to 0. Similarly, y dot y bar is equal to 0. Similarly, z and z bar is equal to 0. Okay. So this will give you x bar, and we can do much simplification on this. So this will be y z bar e or zy bar. Okay. So this is basically the output of this of this function. Okay, can we draw it? Yes, we can draw it. It's simple. So we need one OR with three inputs. One of them is X. The other came from two AND gates. So let's do that. So this AND gate here would have Y Z bar, and this AND gate would have ZY bar. And here is F. Okay. So let's see if we have another example. Yeah, we don't have other. So this is basically, very good examples on how to use manipulation to, reduce or to minimize the circuit. Okay. And we minimize the circuit to get simpler, circuits with less number of gates, less number of inputs per logic gate, so we can reduce the cost and reduce the power consumption of the circuit. Okay, so thank you very much, guys, for attending this lecture, and see you in lecture 4. Bye bye.